So a common thing that needs to be done in many designs is debouncing a mechanical switch. There are many ways of doing it. Um, Here's a few old school ways that I can show you how they work using LT Spice. And then a fourth little thing down here um, that I kind of like, um, and what some of the pitfalls are of doing one of those designs. But here's the switch setup. It's a single pole double throw switch. The switch in one direction goes high to that pole. The switch in the other direction goes high to that pole. And getting it to work in a way that shows what would be switch bounce. I tried a bunch of different ways. Piecewise linear seemed like the best way to go. So this is my switch with bounce built into it. A real straightforward way of doing it is just filtering out the chatter with an RC low pass filter. There's some pitfalls in that. You wanted to use a comparator or some kind of Schmidt trigger, and you gotta select your components very carefully based on the characteristics of the switch and the characteristics of the Schmidt trigger. Its high and low levels, its hysteresis. You're going to want something with hysteresis just so you don't get chatter during the switching time, as the rise and fall times on the RC can be slow. So that is one method. The other method is cross-coupled NANDs to make a set-reset flip-flop. And it turns out getting those to work in LT Spice can be a little tricky. So it took me a minute. I thought maybe my brain had lost all capabilities because it wasn't working, and it seemed like there was no reason. So I don't know if this was the best way to do this, but I played around with the characteristics of the NAND gate, and I ended up having to force some initial conditions on Q and Q naught in order for this thing to actually run the way a real cross-coupled NAND would run. So that was, this part of it was just me experimenting with why the heck isn't this working in my simulation. In this, there's a table as to what the states on a cross-coupled NAND set-reset flip-flop should be. So I connected that configuration into my switch that has bounce characteristics as they close. When the switch opens, there's no bounce. When they close, the contacts hit and it bounces. So that's how most mechanical switches are going to operate. The other way of showing this in a simulation is LT Spice has a SR flip-flop built in, and it sets and resets on a positive polarity instead of a negative polarity, and so thus there's these inverters. It might look a little funny, but these are the ground reference on the inverters. Let me just drag that down there. And so those are the three ways: LC filter, cross-coupled NAND, or an SR flip-flop. This is not a circuit down here that I would use for debouncing a switch, although depending on the switch, it might be something that could be used for that. But we'll get into that a little bit more. Or maybe I should just do that first. This is a one-shot configuration where a asynchronous signal comes in and gets synchronized to a system clock. And this works on a rising edge. So when it goes from low to high, it clocks the D flip-flop, clocks in the 5 volts, goes high. On the clock, that high propagates through, and when you have asynchronous signals on the D input of a flip-flop, you can experience something called metastability, where the if the data transitions at exactly the same time as the clock, you can get oscillations on the output. Theoretically, that oscillation can last for a very, very long time. Basically, it would never stop until something forces it to stop. My understanding is, in reality, that just doesn't happen. The metastability, the oscillations die out pretty quickly. But you would get multiple events out here instead of just the single one that you're looking for. And the most common way of handling that is just putting a second stage so that the transitions that are being experienced here have stopped by the time the next clock cycle comes through. And when that high level clock propagates through, it wraps back around and clears this flip-flop, and everything starts over. So let me execute the simulation, and then we'll take a look at what a couple of things have done. So let's start down here with the one shot, since that's the last thing I was talking about. And I have my piecewise linear starts low, and then I get these what I call, like a switch chatter that goes through, and I just to make it nice, to make sure that I wasn't having trouble with the flip-flops, I ran it through a Schmidt trigger, and it kind of squares those up a little bit. Let's zoom in on one of those. And so there's some artifacts in the simulation, but mostly you get nice edges. And on the very first rising edge, let me do it like that. So on this very first rising edge, you're going to see this go from low to high right here with a, I put in a propagation delay of 1 millisecond so we could see that delay. So the clock is here, the output changes 1 millisecond later. And then if I take a look at, let's I was in the wrong screen. So if I take a look at this clock, I delayed the clock so it would be real obvious when it started. So the clocking actually started here, and so you can see the output doesn't change until the clock starts, and this will propagate through on the next clock pulse. So if I put them both up there, we'll zoom in on that, and the clock, you can see one changes on the first rising edge and then the next stage on the following rising edge. And it this one will go low as soon as the Q output of A18 goes high. So that's what happened there. So you see, and this output with a delay of 1 millisecond went low after the output went high. And so that's basically how a one-shot operates. And let's go now to looking at how the switch bounce part of this simulation works. I have a switch going from low to high. So this one is when it goes high, this switch closes. And so the way it looks on here is this switch was high because it was open, and when it closes, it goes low to ground, and it bounces before it stays ground. And then the other side is on the other opposite edge, does the same thing. The actual switch bounces when it closes, and then when it's done it goes to ground. So here's so one is the set going low and the other one is the reset going low. And if I look at Q, when set goes low right here, hold on a minute, right here, yeah, okay, I got lost. Okay, when set goes low, the Q output goes high, and of course the Q not output goes the other direction, and then on the other side of things, when the reset goes low, the outputs change state again. And if I zoom in on that, reset is this guy right here, and as soon as that goes low, the outputs change. And the thing about those is there is no chatter on the outputs from the switch bounce. So if you just look at those, you just get a nice transition without any switch bounce. And this is just, I'll just show you real quick. This is just me putting something together so that I could understand why it wasn't working. So this is really basic. There's a pulse going low here, there's a hold period, and then there's a pulse going low here, and then a hold period. And the outputs transition accordingly. Then real quick, we have the low-pass filter technique. Again, we have the switch bounce. To isolate that from the RC network, I put in a Schmidt trigger. And so it just propagates through. What's interesting, let's see, why is that interesting? Just some simulation artifacts. But those will all get filtered out by the RC network. So if you take a look at what's on the other side of that, it just kind of ratchets its way down to 0. And on the output, when it gets below the what is it going to be? I'm going to, like 1.5 volts. It should change state. So yeah, right there at 1.5 volts it went low. And then on the other side, reset, we'll do the opposite. Well, let's do this real quick. So you can see all of the switch bounce is gone on that. And then go in the other direction, on the reset side, you'll see the same thing in reverse. Got that, and then you got it ratcheting down on that one, and then again the switch bounce is gone. So those are about all I think I was gonna show. Not sure anyone is gonna care, but I share these things, and sometimes I'm surprised at what people find interesting. So here you go. There's some ways of doing old school switch debouncing, and how to do a D flip-flop one-shot circuit, which is generally discouraged in most real designs because of this metastability problem, for one thing. But if you want to use it, there can be some interesting variations that you do with this type of basic design, that with modifications. There's all kinds of possibilities. So that's it. I will be doing another video pretty soon, and we'll see how the interest in these LT Spice things continues or not. That's it.